Hello dear friends, welcome to my channel. Today's discussion is semiconductor devices and semiconductor device and diode. The variety of semiconductor device available to the technician and engineer is prodigious. Included are rectifying, regulating, tunnel, light emitting, light sensing, switching, rectifier, microwaves, diodes. Diodes are used for converting alternating current to a unidirectional current and regulating voltage levels, detecting and mixing RF signals, switching, clamping in displays. In the generation of microwave power, some devices based partially on diode action are the silicon controlled rectifier, unijunction transistors and the unijunction transistors. The SCR and UGT find wide use in controlling efficiency power delivered to a load. So electrons appear to exhibit a dual nature, behaving as particles at one time and as waves at other times. The particle picture is useful in describing the operation of transistors and most diodes for a few devices, such as the tunnel diode. The concept of electrons being wave-like in nature seems best suited for describing their operation. Atomic structure. According to the particle picture, the structure of an atom is analogous to a miniature solar system. In the center of the atom is the nucleus, which contains positive charge particle called protons. And for many atoms, electrically neutral particles referred to as neutrons. Rotating around the nucleus are electrons, which have a negative charge because the number of electrons equal the number of protons have a negative charge because the number of electrons equal to the number of protons. The atom is normally electrically neutral. The mass of the proton and neutron is approximately the same. The mass of the electron is 1 by 2000 of that of a proton. The simplest atomic structure in hydrogen depicted in the two-dimensional sketch. You see my hydrogen atom I have already created and animated it. Atomic number Z is 1 because a single electron orbits around a nucleus containing a single proton. The orbit or shell nearest the nucleus can hold no more than 2 electrons. Helium, for example, has an atomic number Z equals to 2. Now friends, you see that silicon is Z equals to 14, and you have already seen. So silicon for semiconductor devices is grown to have a single crystal structure. Is simple terms, a single crystal has an ordered array of atoms in absolutely pure or intrinsic silicon. Each atom share an electron with 4 neighboring atoms. As the type of electron sharing results covalent bonds. Okay, I have already drawn a covalent bonds because only the valency of the electrons are involved in covalent bond. The silicon atom is represented simply by four valence electron around nucleus of 4 plus 4 positive charge for electrical neutrality. The resistance of semiconductor is greater than that of a conductor, but considerably less than that of an insulator with aid of the energy bond diagram. According to the modern atomic theory, the energies electron in a material such as a silicon are grouped in energy bands. The valency band of energies corresponding to electrons that are attached strongly by the nucleus. As a result, these electrons cannot serve as carriers of current. To become carriers of current, the electrons must occupy a higher band of energies, referred to as the conduction band. No electron, however, can ever occupy a region referred to as the forbidden band of energy. Okay, so forbidden band, also see the diagram. So which separate the valency and conduction bands. An electron in the valence band therefore must have minimum energy before it occupies the conduction band. The minimum energy is the energy gap of the material. For conductors such as copper, the valency and conduction bands overlap. Okay, consequently there is a plentiful supply of electrons to serve as carriers of current. In an insulator such as a diamond, the energy gap is so great that there are virtually no electrons in the conduction band. The energy gap of semiconductors, however, is such that some electrons are found in the conduction band. An electron, an electron that has reached the conduction band of energies in semiconductor leaves a vacancy or hole in the valency band of energies. Okay, energies. energies. What is interesting is that the whole behaves like a positively charged particles whose charge is equal the opposite to electron. It is influenced by an electric field like an electron but travel in opposite direction more slowly than an electron because of the effects of energy such as heat, light. Equal numbers of electrons and holes are produced in a semiconductor. This action is referred as intrinsic generation of electron hole pairs. As the temperature of a semiconductor rises, the elect electron hole pairs. As the temperature of a semiconductor rises, the electrons in the valency band gain energy and the generation of electron hole pairs. Now I discuss doping. Doping is an intrinsic silicon which contains equal number of electrons and holes is useless for semiconductor devices. One needs to alter intrinsic silicon so that it has either an excess of electrons of holes. This is accomplished by introducing suitable impurities in the silicon. The process is called doping and impurity is referred to as a dopant. N-type silicon. Okay, you have already seen N-type silicon, and now you see, assume that an impurity such as a phosphorus and which has 5 valency electron is introduced in silicon. The impurity concentration required the semiconductor, okay, device. You see that when we dopant is is phosphorus, that is n type, and p type when dopant atom is +3. Okay, when it is p type, dopant atom is p type. So p type assume that the element having 3 valencies electrons, trivalent element. Okay, now I discuss junction diode. Junction diode is the simplest semiconductor device. Is the junction diode. Its basic physical construction and electrical symbol. The junction diode is formed by doping in half of intrinsic silicon with p-type dopant, and the other half is n-type dopant. The boundary at the p and n junction regions which where all the action occurs is called PN junction, and connection made to the P and N regions are referred to as the anode and cathode respectively. Okay, anode and cathode respectively. You see there is a depletion region, depleted of carries. Anode is made negative and with respect to the cathode under the condition diode is reverse and back and biased, and minority holes and electrons near the junction are initially attracted to the negative and positive terminals of the battery and respectively. As result, the junction becomes depleted of carriers. No further current flows. This region of depleted carriers is referred to as a depletion region or layers. The depletion region in PN junction, it forms when n-type and p-type semiconductors are joined, causing diffusion of charge carriers and leaving behind immobile ions. The region is characterized by an electric field that opposes further diffusion and creates a potential barrier. So friends, there is a formation is diffusion. When p type n type semiconductor are brought together, holes from the p side diffuse to n sides and electrons from the n sides diffuse to p sides. Recombination, this diffusing charge carries holes and electrons recombine near the junction. Ionization, these recombinations leaves behind ionized dopant atoms. Depletion region, the region contains these ionized atoms and devoid of free charge carriers is the depletion region. Okay, now it is the junction diode diagram and electrical symbol construction. Okay, so potential characteristics of the diode: lack of free charge carries. The depletion region is characterized by the absence of free electrons and holes. An electric field, the separations of charge due to the ionized dopants creates an electric field across the depletion region. And potential barriers, the electric field creates a potential barrier that opposes the further diffusion of charge carriers. And the width of the depletion region is typically on the order of a micron, 10 to the power minus 6 meter. In essence, the depletion region acts as a barrier preventing the free flow of charge carries across the PN junction, and it's crucial for the operation of semiconductor diodes. Now you see the junction diode, and now you see reverse biased and forward bias. Okay, reverse bias and forward bias. Reverse bias and forward bias I will discuss PN junction. This is the in reverse bias PN junction, the positive terminal of voltage source is connected to the N type semiconductor, and the negative terminal is connected to the P type semiconductors. Okay, you see that the positive terminal of the voltage source is connected to N type. It is the reverse bias. And forward bias, positive term the positive terminal of voltage source is connected to the P type semiconductors, and negative terminal is connected N type semiconductors. This is the forward and reverse bias. And connection depletion regions and reverse current. Okay, reverse bias produce reverse current, while the depletion region widens a small reverse current, typically in the microampere range flows due to the movement of minority carriers. And depletion region, the connection cause the majority charge carries pulled away from the junction and widening the depletion region. This is the reverse bias case. In case of reverse bias, now friend, diode characteristics. Diode characteristics is very important. In the we saw the junction diode behaves like a valve. When forward biased, the diode permits current to flow. In the reverse biased state, it prevents the flow of current. If it were possible to make the perfect or ideal diode, its characteristics might appear shown the figure. You see the figure where it is characterized. It is the for ideal diode, and another is physical diode. This diagram is for a physical diode. And VBR is the reverse breakdown voltage. Okay, reverse breakdown voltage. Now we see a typical characteristic curve for a physical diode appears in forward bias for voltage less than the threshold voltage Vt, and virtually no current flows. Okay, virtual no current flows. In reverse bias, a minute reverse current in order the amperes for silicon. Now friends, I discuss, you see the diode characteristics. You see that D forward current. You see the information carrying signal that superimposed onto carrying signal during the process of modulation. Okay, you see the diagram. So there is the three message signals, the modulation signal also known as message signal. You see the diagram modulations, and this is a basic circuit. And here is a, you see one is rectified output, another is sinusoidal input. Okay, sinusoidal input. This is the modulated signal. Here IF is equal to D forward current. This is the basic circuit. Okay, and now friends, this is the characteristics of the circuits. When diode is forward biased, current IF flows and voltage VF is 0. Okay, voltage VF is 0 regardless the forward current. Note, it is common practice to use V instead of E in denoting voltage for diode and transistor characteristics. This will be the adhered to in this and the describing the characteristics of the semiconductor devices. When the diode is reverse bias, this is called IR. Okay, is 0 regardless of the value of Vr. So friends, I draw some modulation signal. I will show modulating signal obtained from the demodulator and input output waveforms from demodulations. You see input wave and output wave and demodulation signal output input. Okay, so now it is the characteristic. We discuss characteristics of diode. There is a Zener diode. Now I will discuss Zener diode, the reverse characteristics of a physical junction diode. It was noted that reverse voltage increases at a certain level VBR. You have already seen that. You will see the VBR I have already drawn. This is the VBR. The diode breaks down. Okay, VBR means breaking voltage. Okay, voltage is breaking, reverse breakdown voltage. Okay, reverse breakdown voltage, the diode breakdowns in the operating region of reverse current from the IZK to IZM. The voltage across the diode is essentially constant, and current, the knee current. Okay, IZK, the knee current. Okay, you can see this way. Okay, knee current in the minimum current. There is a minimum current and the maximum current limited the device distributions. Okay, distributions. So the voltage below the knee is the Zener voltage of the device. Zener voltage of the device, and over the operating range of reverse current, the voltage across the diode is nearly constant and equal to the Zener voltage. Diode made to exhibit specific Zener voltages are referred to as a Zener diodes. Their symbol, Zener diodes are available having Zener voltage of approximately 2 to 200 volts. A major application for Zener diodes is their voltage regulators. A model of Zener diode you will see. Thanks for watching. I hope I give some little bit ideas.